Okay. Hello. Good morning, everyone. Okay. Bharat is there. Ritvik, Shruti, Purvik. Okay. See, today in this session, we are going to um, discuss about a few concepts of various chapters. Okay, which actually helps you in the coming KVVY as well as JEE Mains exam. Okay, since it is actually a quick revision class, we'll see some problems also into this. So obviously, we are not going into all those theory and small details, right? So we only discuss those concepts which is helpful and which it requires. Okay. So so Kirt Vaishnavi, fine. You see, first of all, last class I had taken a division class also of chemical equilibrium. Okay, and there I again did not discuss about Lee Chatelier's principle. Okay, so first of all, we'll discuss today Lee Chatelier's principle. Obviously, there are some 11th class students also there, so they haven't done this before, Lee Chatelier's principle. But some 12th class students, you must have done this, right? Okay. So chemical equilibrium, we also discussed a little bit of ionic also. Buffer solution we'll discuss in this session, okay, after this. And then we'll discuss the concept of equivalent mass. And last we'll see the concept of GOC, because GOC we have too much. We cannot cover everything obviously into this. A few concepts of GOC also we discussed in the last. Okay, so let's see. Let's start with Le-Chatelier's principle. Okay, so the Le-Chatelier's principle, if you see the definition of this Le-Chatelier's principle is what? Whenever a system is in equilibrium, right? Whenever any reaction you have, and that reaction is in equilibrium. Okay, so if you change the equilibrium condition, right, or the if the equilibrium condition of any process is subjected to change, then the equilibrium shift into that direction where where the effect of change will be minimized. Okay, so what I said just now, that whenever a system whenever a system in equilibrium is subjected to change its equilibrium condition its equilibrium condition then the equilibrium shift shifts in that direction by which the effect of change effect of change is minimized. Okay, this is what the Le-Chatelier's principle we have. One more thing I tell you, 12th class students, if you have since you have done this before, so whatever you feel important, you can write down in your notes. Everything is not important to write. Okay. Second thing, for suggestion for 11th class students, if they write it properly, it will be helpful for them. Okay, because this particular portion, Le-Chatelier's principle, I won't do again in the class. Okay, so better if they write the notes properly. Okay, so now you see. What is the meaning of this? When I said that equilibrium shift into that direction by which the effect of change will be minimized. Simple example, if I take here, suppose we have a reaction, any reaction we have, and in that reaction, if I am increasing the concentration of reactant, right? Example, if reactant concentration is increasing, square bracket I'll put here, concentration of reactant is increasing, then the equilibrium shift or the reaction goes in that direction by which the concentration of reactant will decrease, right? The two directions are possible, either forward or backward, right? Two directions are possible, either the reaction goes into forward direction or backward direction, right? When we increase the concentration, so if the reaction goes in forward direction, then the concentration of reactant will decrease, correct? And if it goes in the backward direction, the concentration of reactant will increase. So that's what Le-Chatelier's principle says. Whatever the change you have done, the equilibrium shift in that direction by which the change that you have produced, that change will be minimized. Okay, so obviously when you increase the concentration of reactant, the reaction proceeds in forward direction, like this. Okay. Right. So this is the meaning of Le-Chatelier's principle. Okay. One by one, we'll discuss what is the various factors we have into this. Okay. So first factors, if you see into this, that is the effect of change in concentration. Right. The first one, if we see the effect of, there are 4 or 5 different cases we have here that we'll discuss. Effect of change in concentration, change in concentration, and concentration of reactant or product, reactant or product. Okay. Now you see in this, as I said just now, I have taken the example, and we can write direct here that if concentration of reactant, square bracket I have written, it means concentration of reactant. If concentration of reactant increases, reaction goes in forward direction. Second case possible, if concentration of product, sorry, concentration of reactant decreases, reaction goes in backward direction, right? Because concentration of reactant is decreasing. So reaction will come into the backward direction so that it will increase the concentration of reactant, right? Again, the second, third possibility is what? If concentration of product increases, then again the reaction goes in backward direction to decrease the product of the reaction. And if the concentration of product decreases, then the reaction goes in forward direction to increase the product of the reaction, concentration of product. Okay. Yeah. So this is the four possible cases. It is very straightforward and simple. Okay, you can understand this easily. Now the next condition we have, or the next factor, is the effect of temperature. What happens if we change the temperature? Effect of temperature, right? Temperature effect will actually understand by the nature of the reaction. Nature, if I say, it means whether it is exothermic or endothermic, right? So first of all, the effect of temperature you can understand by this particular what we say equation, which is Van 't Hoff equation. Log K2 by K1 is equals to minus del H divided by 2.303 R into 1 by T2 minus 1 by T1. With this, you can understand. And one more thing that you probably know, that if K increases, reaction goes in forward direction. More value of K, more the tendency will be in forward direction. If K decreases, the reaction goes in backward direction. This we already know, right? Now here you see, if I'm since I like I said, the effect of temperature we can understand by the nature of the reaction, if it is exothermic or endothermic. So suppose I'll take the both condition one by one. First, I am taking, suppose, endothermic reaction we have. Okay, suppose the process or the reaction is endothermic. Endothermic. The first one I'll do in a little bit of in detail. Similarly, you can do for the other cases also, right? Now you see, for endothermic reaction, we know del H is greater than 0. This we know already. Okay. We have to see that in endothermic process, if we increase the temperature, then what effects on K takes place? Whether K value increases or decreases, that you have to understand, right? So now you see, endothermic process we have del H greater than 0 as temperature increases. As temperature increases, which means what? This particular reaction says, this particular equation says K2 is the equilibrium constant at temperature T2 and K1 is the equilibrium constant at temperature T1, right? Okay. So if temperature increases, which means what? I am taking the condition of T2 is greater than T1. This is the condition I am taking. right? Condition can be anything. We are discussing all possible cases, right? So as temperature increases, means T2 is greater than T1. Now you see, if I reverse this, because we have to find out this 1 by T2 minus 1 by 2. You see one thing here, what is the objective here we have? See, del H is greater than 0. So this del H is positive, right? This value is positive. Del H value is positive. This is negative. So positive, negative, negative. If this value is negative or positive, that will actually decide whether log K2 by K1 is greater than 0 or less than 0, right? So since one particular type of reaction will fix the value of del H, whether it is positive or negative, according to this term minus del H by 2.303 R will have either positive or negative. So in this case, it is negative. You see, positive plus minus minus, positive, negative, negative. So in this case, it is negative. Now, depending on this value of this, whether it is greater than 0 or less than 0, we can say log K2 by K1 is less than 0, greater than 0, right? So that is what we are going to discuss. So condition I have taken T2 greater than T1 when temperature increases. So what we can write, 1 by T2 is less than 1 by T1, and hence 1 by T2 minus 1 by T1 is less than 0, right? Which means this value is negative. So when this value is negative, you see, and this is already negative, so negative, negative, positive. So what we can write under this condition, log K2 by K1, log K2 by K1 is greater than 0, right? Which gives you log K2 minus log K1 is greater than 0, and further K2 is greater than K1. This is the conclusion we get here. So what we can say in endothermic reaction, as temperature increases, equilibrium constant increases, right? When T2 greater than T1, K2 is also greater than K1. So that is what the effect of temperature we have in endothermic reaction. Okay, just write down one line over here after this, that in endothermic reaction, in endothermic reaction, as temperature increases, equilibrium constant K increases, and when K increases, reaction goes in forward direction. Is it clear? Let me know. Okay. Now in endothermic reaction only, we can also understand the second possibilities. Like the first one I took, that as temperature increases. This is also possibility as temperature decreases. This is also the second possibility we have. So in this case, the similar way you can conclude T2 less than T1, 1 by T2 is greater than 1 by T1, then 1 by T2 minus 1 by T1 is positive, right? So there if you see, as temperature decreases in endothermic reaction, K value also decreases. And when K value decreases, the reaction shift into backward direction. Reaction shift into backward direction. Okay, so this is the two possibilities we have in endothermic reaction. Similar kind of possibilities are also there in case of exothermic reaction, when the reaction is exothermic. So exothermic reaction means what? Del H is less than 0. This is the difference. Okay. So now you see when del H is less than 0, you see this one, the first page that we have done. Here you see del H less than 0 now we have. So this is negative and this is already negative. So this negative, negative, positive, right? So if T2, 1 by T2 minus 1 by T1 is negative, log K2 minus K1 is negative. If it is positive, log K2 minus K1 is positive. Correct? That is what we are going to do next. So you see, del H is less than 0 if temperature increases, if T increases. This means what? T2 is greater than T1. So 1 by T2 minus 1 by T1 is less than 0. Okay. This means log K2 by K1 is again less than 0 and K2 less than K1. This means equilibrium constant decreases, the reactions shift into backward direction. So in exothermic reaction, as temperature increases, backward shift possible. Reverse of this will be true when temperature decreases. So if temperature decreases, then we can say K increases, and when K increases, forward shift will be there. Forward shift. Okay. So this is the 4 different cases we have in exothermic endothermic reaction. Okay. The third case here we have, third case I'll take, and that is effect of pressure. Effect of pressure. In this also, there are 3 cases possible, 3 different types of reaction we have. The first one in this, when the reaction which has del Ng value is equals to 0, which has 0 del Ng value. Okay, which means what? The reaction is, suppose if I assume the reaction is this: A gas plus one general reaction I am taking, B gas gives you C gas and D gas. This is the reaction we have, right? Since del Ng is equals to 0, so we have to find out the effect of pressure in this reaction. Okay, so obviously when del Ng is 0, so what we can write, Kp is equals to Kc, the first thing. Value of Kp and Kc will be same, correct? So if I write down the expression for Kp, that will be what? The partial pressure of C into partial pressure of D divided by partial pressure of A into partial pressure of B, right? Kp, we have to write down the partial pressure. If we write down Kc, then concentration term we have to use, right? Now we know this from Dalton's law that partial pressure is equals to mole fraction into total pressure, Pt. Mole fraction into total pressure. The effect of this pressure only we have to assume, right? The pressure at which the reaction is taking place, the total pressure. Okay. Now you see, according to this formula, if I write down the expression of Kp, that will be what? Partial pressure of C is equals to mole fraction into C into total pressure into mole fraction of D into total pressure divided by mole fraction of A into total pressure, mole fraction of B into total pressure. Okay, so you see here, all this pressure term, the total pressure we have, will get cancelled in the numerator and denominator. This will get cancelled. Okay, and that's why the expression for this will be xc into xd divided by xa into xb. Okay, now you see in this one, kp is independent of pt, right? Kp term is independent of total pressure pt. So whatever total pressure you take, that won't affect kp or this expression. Okay, and that's why we say the reaction in which del Ng is equals to 0, for that particular reaction pressure has no effect in this, no effect in this. Okay, so you can write down, for this kind of reaction pressure will not change the equilibrium condition. Is it clear? Okay, so del Ng is equals to 0, pressure won't have any effect. Next one you see. Now similarly you can write down the all other possibility you can understand. You see the second case I am taking, because in these three cases are possible. First one is when del Ng is 0. Second one I am taking when del Ng value is greater than 0. Right? Del Ng value is greater than 0. For example, suppose if I write A gas gives B gas and C gas. Suppose this we have reaction. Okay, so obviously for this reaction, del Ng value is greater than 0. Number of gaseous product minus number of gaseous reactant. Okay, now if I write down the expression of Kp, that will be what? Again, partial pressure of B into partial pressure of C divided by partial pressure of A. And that again we can write xb into xc divided by xa into pt square divided by pt, right? So obviously this contains what? Xb into xc divided by xa into pt. This is the expression we have here. Okay, see, one more thing here, we can also explain the same thing with some theoretical uh, way also, like when pressure increases volume decreases, so number of moles per unit volume increases. Like that also we can also explain, right? But I think this is the mathematical explanation I'm giving you, that helps you more to understand the concept, right? That's why I'm taking this equation part. Okay, now you see, since kp depends on pressure, the expression contains the pressure term here, right? So obviously the pressure will have some effect on these kind of reaction. Okay, what kind of effect, that we'll see now. Now suppose if pressure increases, if pt increases, then what happens, that we have to understand. Okay, okay, so here you see, if pt increases, so obviously this kp has to be constant, right? Because equilibrium constant depends only on temperature. It has to maintain its value, constant value, right? So if this value is increasing, right, to make this ratio constant, xa should also increase, right? If pt increases, to make kp constant, xa will also increase. xa increases, and when xa increases, xa is a mole fraction of a, right? This mole fraction of a should increase, and mole fraction of a will only increase when the number of moles of a increases, right? And that is only possible when the reaction goes in backward direction. Okay, so I hope you understood this. If PT increases, XA increases, and this is only possible when backward reaction is favorable. So here we have, in this type of reaction where del Ng is greater than 0, as pressure increases, backward reaction will be favorable. What happens if PT decreases? PT decreases, total pressure decreases. No, Niranjan, we cannot say if a PT decreases, then KP decreases. See, KP has to be constant. Okay, Kp depends only on temperature. So with pressure, this value will not change, right? So we have to maintain the value of Kp. So if this numerator is decreasing, so denominator also decreases. So that will maintain the ratio. That's the point here, right? So if Pt decreases, like I write over here, like I wrote over here, if Pt increases, Xa increases. Why this is true? Because this ratio we have to maintain. Pt by Xa ratio we have to maintain, right? So if Pt decreases, then Xa should also decrease. The mole fraction of A should also decrease, and mole fraction of A will decrease when the reaction goes in forward direction, right? So in the case of temperature, we were discussing over there that K value decreases or increases. Why we are discussing about K also over there? Because K depends on temperature. Equilibrium constant depends on temperature. That's why we say if temperature increases, K decreases or increases accordingly, right? But here we are talking about the effect of pressure, and pressure won't change the equilibrium constant, right? Equilibrium constant depends only on temperature. So we have to maintain the value of Kp, and that's why we are doing like this. Okay, understood? Okay, now the same thing we have to do in the last case where the reaction has del Ng value less than 0. Okay, del Ng value less than 0. Suppose the reaction is this: A gas gives C gas, del Ng value less than 0. So what is the expression for Kp we write? It is partial pressure of C divided by partial pressure of A into partial pressure of B, and that further we can write Xc by Xa into Xb into 1 by Pt. Now you tell me here, all of you, as Pt increases, then what is the direction of the reaction? As Pt decreases, what is the direction of the reaction? Both way. Backward as P decreases, forward as P increases, and backward as P decreases. Okay, so if PT increases, obviously to maintain the ratio, XC should also increase, right? And XC will only increase when the reaction goes into forward direction. So if PT increases, forward reaction favorable, and if PT decreases, backward reaction is favorable. Backward reaction is favorable, right? These are the two conditions here. Now, see, on the basis of this temperature and pressure, one question has been asked in previous exam that I'll write you over here. Suppose we have A gas, right, plus 2B gas gives C gas plus heat, right? This is the reaction given, equilibrium reaction, obviously reversible reaction. Okay. Now this reaction, the question is for this reaction, forward reaction is favored. Forward reaction will be favored under which condition? The condition is given low pressure, sorry, low pressure, high temperature. Second one, low pressure, low temperature. Third one, high pressure, high temperature. And fourth one, high pressure, low temperature. Like this, the four reactions are given. Yeah. Tell me the answer of this question. Option D. Where is Bharat? Sukit, Bharat, what is the answer? Okay, Ashutosh is also saying D. Anyways, hello. So first of all, you see this reaction, and this question has been asked previous year. Okay, you see it's very simple. First of all, heat is going out, right? So it is what? It is exothermic reaction. Since heat is going out, right? So exothermic reaction means del H is less than zero, right? So for exothermic reaction, when del H is less than zero, this is favored by what? Forward reaction we have. So we must have K2 greater than K1 for forward reaction. This is also the condition we have to satisfy, right? And this is only possible when 1 by T2 minus 1 by T1 is positive, because this is negative and negative is positive. So 1 by T2 minus 1 by T1 is positive. That is only possible when T2 less than T1, right? So obviously low temperature will be favorable for this reaction, for forward reaction. So either B and D will be correct. A and C are not possible. Okay. Now pressure thing. Pressure thing we can understand by del Ng value. Okay. What is the del Ng value of this reaction? It is less than zero, right? Del Ng less than zero. So just now we have done for del Ng less than zero, as pressure increases, forward reaction favorable, right? This is the condition we have here. So obviously we have high pressure and low temperature. B is also not possible. Option D is correct. Okay, Bharat has left. Okay, anyways. Anyway, so option D is correct, right? So this is how we do the questions of all these Le Chatelier's principle and all. Okay, there are a few more conditions we have, and that we'll see quickly. That is addition of catalyst. You write down addition of catalyst. The second next condition is a catalyst won't affect the equilibrium state. It only increases the rate of forward and backward reaction by decreasing the activation energy. Okay, so write down into this. Catalyst won't affect catalyst won't affect the equilibrium condition. It only increases the rate of forward reaction RF and RB, rate of backward reaction, and helps the reaction to attain the equilibrium state sooner. Okay, that is the addition of catalyst. See, catalyst, we are assuming positive catalyst here, right? If the catalyst is negative, right, then that will increase the activation energy. This catalyst is positive, we are assuming. If the catalyst is negative, that will increase the activation energy and decreases the rate of uh, forward and backward reaction, and then the equilibrium will attain after uh, after long time. Okay, comparatively more time we'll have to wait into that. So if you see the graph over here, the graph we have in this case, suppose this is the graph we have for any reaction. Okay, obviously this is for reactant and this is for product. Okay, so this graph, the yellow one, is without catalyst. Okay, now the same reaction is taking place with the help of a positive catalyst, and the reaction goes like this. At it lowers the activation energy. The initial and final position will be same, right? But this green one is with positive catalyst, and if the catalyst is negative, if the catalyst is negative, that catalyst will increase the activation energy, and then the reaction goes like this. It will increase the activation energy and then comes down to the final value here. Right, so this blue one is with negative catalyst. So both is possible. Equilibrium condition will be same, but with positive catalyst, it attains sooner, and with negative catalyst, it takes long time. Right. So that is what you see. This is the decrease in activation energy with positive catalyst, and this is the increase in activation energy. So when this value decreases, the rate of forward reaction will be more, and rate of backward reaction will also be more. But when this value increases, rate of forward reaction uh, will be less. You see, large is the energy difference here. So we have to the rate of forward reaction, backward reaction, both will decrease in that case, and hence the equilibrium attains after a long time. That's the meaning. Which one? Which one you didn't understand, Pushpinder? Okay, catalyst effect. See, catalyst effect is nothing. First of all, catalyst won't affect the equilibrium condition, right? Suppose A and B reaction we have, right? A and B we have some reaction, and here is the equilibrium condition we have somewhere in between, right? So this is the forward reaction, and this is the backward reaction we have. So after some time, this equilibrium will get into this, right? But if you have catalyst, right? So catalyst does not no do anything over here. If the catalyst is positive, then the rate of forward reaction will increase. RF will increase over here, right? It only increases the rate of forward reaction and backward reaction. The rate at which A is converting into B with positive catalyst, this rate will increase, and the rate of B also will increase. So both reaction, whether it is forward direction reaction or backward direction reaction, is going with a faster rate, right? And that's why we attain the equilibrium sooner, right? Or with a less time, right? It requires less time to attain the equilibrium state over here. The condition of equilibrium will not change. Neither this initial and final state will change. That will also be same, right? But initially, without catalyst, if the equilibrium is attaining after suppose 10 minutes, then with positive catalyst, this time will only decrease and it will be anything less than 10 minutes, right? And that's why we say with positive catalyst, the rate of the time at by which the reaction, the equilibrium is attaining, that will be comparatively less. Okay, why it happens? Because the activation energy decreases, right, with positive catalyst. This is the activated complex, and activated complex forms here with positive catalyst at a lower energy only. This is the energy axis, and this is the progress of reaction. X-axis is the progress of reaction. Y-axis is the energy axis we have. So energy of activated complex will increase. So if this energy difference, which was initially from here to here, between reactant and the activated complex, now with positive catalyst, the energy difference is this only. So less energy difference, so it can cover it easily, and that's why the rate of forward reaction is more. And reverse is true when the negative catalyst is there. Okay, so anyways, this is the effect of catalyst we have. Now next, and this is important also, this question they have asked many times. Okay, addition of catalyst, you must keep in mind equilibrium condition will not change, but equilibrium attain with a faster rate if catalyst is positive. Now write down effect of introduction of inert gas. Effect of introduction of inert gas, the last condition we have here for Lee Chatelier's principle, and that you write down addition of inert gas. This is possible in two different cases again. We can add or introduce this inert gas at constant volume and constant pressure. Okay. So first condition you write down, if you are adding this inert gas at constant volume, at constant volume, right? So at constant volume, write down there is no change in the concentration of, at constant volume, there is no change, no change in the concentration of reactant or product, right? no change in the concentrated reactant and product, and hence inert gas, hence there is no effect, simply I write down, okay? Hence there is no effect at equilibrium, at equilibrium, right? So when you add an inert gas at no at at constant volume, okay, so that will not change the equilibrium condition. Example, you see, suppose I have taken this reaction, A gas plus B gas gives C and D, right? Now in this, what we write, the Kp value is equals to what? The Kp value is equals to partial pressure of A into partial pressure of B divided by partial pressure of C into partial pressure of D, right? Now in this, suppose if you add an inert gas, right? Inert gas we are adding into this, whose number of moles is N, right? N moles of inert gas we are adding, right? If this will change the partial pressure of this individual component A, B, C, and D, right? Then Kp value will change. If the partial pressure will not change, Kp value will also not change, right? So if I write down the formula of partial pressure, that is P, suppose A we are calculating, partial pressure of A, that will be equals to what? Mole fraction into total pressure. Mole fraction, what we can write? It is number of moles of A by total number of moles, that is Na plus Nb plus Nc plus Nd plus the number of moles of inert gas, N, right, into. What is the pump total pressure here? That will be total number of moles Nt RT divided by V volume, right? This is the partial pressure we have when we added N moles of inert gas. This is the inert gas, number of moles of inert gas we have. When we haven't added this inert gas, what is the partial pressure then? It will be PA RT by V, and PV is equals to nRT we are using. So this is the partial pressure when there is no inert gas. Now when we have added this inert gas, right? So what happens here? This is very clear from this reaction, from this equation, that NT that you have here, this is the total number of moles, right? Which includes what? Which includes inert gas also. And what is this value in the denominator? This value is also the total number of moles, which is nothing but NT, right? So obviously this and this will get cancelled, and the partial pressure again you get here, that will be Na RT by V, which is exactly same that we had earlier when there is no inert gas added, right? So whenever we add this inert gas, the the Kp value will not change, since the partial pressure is not changing if the volume is constant. We are introducing the inert gas at constant volume. This is the first case we have. Second case we'll take at constant pressure, okay? So whenever we say, since you see the partial pressure initial and final is same, what we conclude from this, that at constant volume, addition of inert gas won't affect the value of Kp, hence it has no effect at equilibrium. Understood this? Okay. Now The second condition we are taking addition of inert gas at constant pressure. Sorry, I forgot to write here at constant volume this is, and this is at constant pressure. Okay. Now in this also at constant pressure, this is the last case we are discussing. We have three cases possible. We'll do this quickly. Once you understood the first one, you'll understand the other one also. See, the first case here you are taking, that is when del Ng is equals to 0, right? And since the pressure is constant, so we have to see the effect on equilibrium when change in volume is there. Since we are adding inert gas, so that will change the volume, right? Total volume will change after the addition of inert gas. So suppose some simple example I am taking, A gas is giving B gas, smaller reaction I am taking. Del Ng is equals to 0. So what is the value of Kc here? That will be concentration of B by concentration A, right? Concentration means what? Number of moles by volume divided by number of moles by volume. Volume gets cancelled. Nb by Na. You see, this Kc is independent of volume term. Independent of volume. Hence, addition of inert gas addition of inert gas won't affect equilibrium if del Ng is equals to 0. See, one thing you have to understand here, we are adding inert gas at constant pressure, right? So pressure is constant, that won't change. Okay, but since we are adding inert gas, that will change the total volume. So if Kc is independent of volume term, then whatever the change in volume, that won't affect Kc. That's why we are looking at the volume term over here. Now, this one you see, if I take the second case into this, and that is when del Ng is greater than 0. Suppose the reaction is this: A gives B and C. Okay. So for this, Kc will be what? It will be concentration of B, concentration of C divided by concentration of A. So this gives you Nb into Nc by Na into 1 by V. This is the expression you get if you solve this. Because concentration is mole per liter. Mole per liter, here we have V square and here we have V. So that will get cancelled, we'll get V. Okay. Now, since we are adding inert gas, right? So volume increases. So what happens here, as volume increases, right? As volume increases, then what happens? This we are increasing. Kc value will not change because again it depends on temperature. So if this volume is increasing, so to maintain the ratio, this Nb Nc value should also increase, right? And that is only possible when the reaction goes in forward direction, right? So as volume increases, moles of product, number of moles of product should also increase to maintain the ratio, and that is only possible when the reaction goes in forward direction. Is it clear? Del Ng less than 0. A gas so for this, if you write down Kc, that will be number of moles of C by number of moles of A, number of moles of B into V. So as volume increases, right, Na, Nb, Na or Nb should also increase to maintain the ratio, and that is only possible when the reaction goes in backward direction. Is it clear? Done? Okay. So these are the few, all possible cases we have discussed for Le Chatelier's principle. Now we'll see some questions which has been asked already on this Le Chatelier's principle. Okay. So you see the first question on this, and the question is this: the reaction is given, and the reaction is N2 plus O2. N2 plus O2 gives 2NO plus heat. This is the reaction given. Now, in the above gaseous reversible reaction, all these are gases, gas, gas, and gas. Gaseous reversible reaction. If the pressure increases, if pressure increases, then what is the effect on Kp, equilibrium constant? What is the answer? One more question, let me write down. N2O4 gas gives 2NO2. At a fixed temperature, the volume of the reaction container is halved. Container is halved. For this change, for this change, which of the following statement is correct? Option A. Neither Kp nor alpha changes. Option B. Kp alpha both changes. Kp changes, alpha constant. Alpha won't change, means Kp constant, Kp constant, alpha changes. What is this possible into this? Okay, so first one is pretty clear that del Ng value is 0, so Kp will not have any effect, right? So that is correct, no effect. Second one, you tell me, what is the answer? Kp and alpha. Niranjan is saying D, Sukir is also saying D. Anyone else? Yeah, it's right. You see, D option is correct. Why? Because you see, the temperature is fixed, and Kp is what? Kp is the equilibrium constant. So if the temperature is fixed, then Kp won't change. So Kp will be constant. That is true. But since the reaction container is half, that will change the degree of dissociation. This is degree of dissociation. This will change the degree of dissociation. Okay, degree of dissociation. So that's why answer is D. One more question you see here, and this question was asked in JE Advanced. Okay, so you see this question, the last one for this, then we'll move on to the next topic. The reaction is given CaCO3 solid gives you CaO solid plus CO2 gas. This is the reaction. Now in this, for this equilibrium, the correct statements are is or are, whatever it. You may have more than one answer also possible. Okay. The correct statement you have to find out, and options I am giving you. Okay. The options are del H, that is the enthalpy of the reaction, depends on temperature. B. K is independent of initial amount of CaCO3. C option. K depends on the pressure of CO2. Pressure of CO2 at a given temperature. Option D. Del H is independent of catalyst, if any, if it is present. B, C, and D. B, C. So does alpha increases or decreases with decrease in volume? Okay. One question that Vaishnavi has asked. So does alpha increases or decreases with decrease in volume? Okay. So volume decreases means what, Vaishnavi? Volume decreases means concentration increases, no? Right? As volume decreases, then concentration increases, and that will increase the dissociation of alpha. Right? More concentration will be there, so more will be the dissociation, no? So that you will attain the equilibrium. See, like this also you can understand. See, you can easily understand this. If you write down the expression for Kc, right? If you write down the expression for Kc for any reaction which has del Ng greater than 0, right? So del Ng greater than 0 will be what? Can be like this. It is, concentration of B, concentration of C by concentration of A. So concentration of B and C, NB and C by Na into 1 by B. Right. So if this volume decreases, the number of moles of B and C will also uh, decrease, right? If this volume decreases, volume becomes half, right? So number of moles of B and C will also decrease to maintain this Kc, right? So that will also affect the alpha. And when you see this, when Kc decreases, okay, one thing you can understand from this. First of all, you see, okay, I'll just we'll come to this question. We'll come to this question in some time. Okay, first you see this. The question is that if this what we say volume of the container is half, then what is the change on alpha? Whether it is increases or decreases, alpha will change. That is true. But what is the change? Whether it is increase or whether it increases or decreases, right? So that you can understand. Alpha is what? It is the number of moles react divided by the initial number of moles, right? So now if the number of moles react is more, obviously directly you can do from here. If the number of moles react increases, that will increase alpha also. When you are decreasing the volume, let it be, don't write this. When you are decreasing the volume, obviously the concentration of the reactant will increase. And when the concentration of the reactant will increase, that will increase its dissociation constant also. That will increase its tendency to get dissociate also, right? And that is why the number of moles reacted here will be more, and that's why the alpha will be more in that case. Okay, directly you can do from this. Okay, now this question, tell me what is the answer? What is the answer? Tell me. See, why C is the answer? I don't know why all of you are saying C. B is one of the option that is correct, Pratik. Why C? Just a second, I'm coming. Okay, so you see this partial pressure. You see, the question is what? This question was asked in JEE Advance. Okay, multiple choice question. JEE Advance. So you see, first of all, this del H depends upon temperature. It's correct. One equation you must have done in physics also, that is Kirchhoff's equation. Right? Del H value depends upon temperature with this relation. See here, I'll just write down. The answer in this question will be A and B. This A and this B is correct. This is not correct and this is not correct. Del H, suppose del H you have to find out at any temperature T2. And if you know the value of del H at temperature T1, del H is equals to, as T2 is equals to del H at T1 plus del Cp into T2 minus T1. This we call it as Kirchhoff's equation. It is probably given in physics. Okay. So first of all, the enthalpy change depends upon temperature, what temperature you are taking, right? Okay, I'm coming to that one. So, and this B is obviously correct, right? K is independent of initial constant, initial amount of this, right? So B is correct. Coming back to this C, K depends on partial pressure of CO2 at given temperature. K depends only on temperature. It won't depends on partial pressure of any of the component. Correct? This means what? When you change the temperature, according to partial pressure, K also changes. Right? But partial pressure has no role into this. So K depends only on temperature. Option C is not correct. Del H is independent of catalyst. Del H is not independent of catalyst because you see the activation energy for forward and backward both decreases. Right? See, this value is also decreasing and this value is also decreasing if the catalyst is positive. So that will decrease in such a manner so that the del H will be constant. It is not like the rate of forward reaction or the energy difference between the activated complex and reactant is decreasing. So this energy is also decreasing with product and this. Which one? Which one, Ritik? Sukit, now I'll discuss one small concept of buffer solution in ionic equilibrium. Yeah. It's the same thing, Ritvik, the same thing. Okay, so kids, we'll start buffer solution that will take around 20-25 minutes, and then last we'll do that GOC. Okay, because GOC there are many things, only specific thing we'll discuss. Did you understand this? Del H depends upon temperature, K independent upon initial amount. Okay, and D option is not correct because both energy is decreasing, right? Since the activation energy is decreasing. Did you understand this? Tell me quickly. Okay. Now next you see we'll start next buffer solution. Okay, ionic equilibrium will have buffer solution. So I know there are many things that you should know before this buffer solution only, but since it is important buffer solution, so I'll give you the discuss this buffer solution only into this. Okay, and then we'll see the you know uh, GOC, some concepts of GOC. Okay, so let's discuss this. What is a buffer solution? Okay, see if you have any solution, right? Any solution you have which has excuse me, some pH value, right? Means either it is acidic or basic. Okay, so what happens if you add an acid into it? We're adding an acid into it. So acid gives what? H plus into the solution. And when H plus we are introducing into the solution, so obviously the concentration of H plus is increasing. And when the concentration of H plus increases, its pH value decreases. Right? Because we know pH is equals to what? Minus log of H plus. Right? If you add base into it, OH minus, so then its H plus concentration will decrease, right? pH will increase, and that gives you basic solution, right? So the point I'm trying to make here it is what? That whenever you add an acid and base into any solution, that will change its acidity and basicity of the solution, right? Buffer solutions are those solutions which, hello? Yeah, okay. I thought some problem was there. Anyways, buffer solutions are those solutions which resist the change in pH. Which resist the change in pH. Actually, you see, uh, like I said here, you're adding acid into it. That will eventually change the pH of the solution. Buffer solutions are those solutions which resist the change in pH, the change in pH on addition of addition of small amount of acid or base into it. Acid or base, it will be. Okay. So any solution if you have, and if you have added a small amount of acid and base, if the solution resists the change in pH, then the solution is said to be buffer solution. See, it resists the change in pH, but it does not mean that the pH of the solution will not change. The pH will change, but the change will be less than the change when the solution is not a buffer solution. Right? Means what? If you have a buffer solution and one is non-buffer solution, if you add equal amount of acid into these two solutions, one is buffer, other one is non-buffer, then the change in pH of non-buffer solution will be more than the change in pH of the buffer solution. So one thing you should be very clear, that it does not mean that the change in pH of the buffer solution is zero. No, it is not zero, but the change is very small, right? And this change is obviously lesser than the change when the solution is not a buffer solution. Is it clear, the definition? Okay. Now you see here, so first thing, it should be very clear, right? Buffer solution pH changes, but that change is not that much. Okay. Now you see the buffer solution, there are mainly actually there are three types of buffer solution, but mainly we have two types that we'll discuss. Right, important. All these three types we'll discuss in the class, right? But two types which are more important that we are discussing today. Acidic buffer. The first one is acidic buffer. The second one is basic buffer, and the third one is salt buffer. Right? Acidic buffer, basic buffer, and salt buffer. So first of all, you have to be very clear, because all those 12th class students, they have done this ionic equilibrium. 11th class you haven't done, but you don't worry. Just try to keep this discussion in mind, because buffer solution is important. If you get some direct question from this in KVPY, you can answer it, right? But again, I'm telling you one thing, there are many other things which we should discuss before this buffer solution, but we don't have time for that much. Okay, so I'm directly giving you the concept of this so that you can understand, right? And most of the, like, 12th class students, they will agree with me that in ionic solution we have many, formulas of pH, calculation of pH, right? There are many formulas of pH. So what formula you have to apply when, that you have to understand. Okay, so keeping this in mind, let us discuss this, and then we'll come back to this. How do we analyze this particular thing, right? Acidic buffer, you see, first of all, you should know how this acidic buffer forms, right? So one thing that you have to keep in mind, acidic buffer forms by the forms by the combination of solution of weak acid. It is the solution of weak acid plus its salt with strong base. Weak acid and its salt with strong base, right? So weak acid, the example of weak acid is, suppose, CH3COOH, and its salt with strong base means what? When this CH3COOH combines with NaOH, so that gives you CH3COONA, right? This is the salt of weak acid and strong base, plus H2O we get here, right? Plus H2O. So whenever you have this combination CH3COOH plus CH3 COO-Na. This forms an acidic buffer, right? Whenever you have combination of weak acid and its of salt with a strong base, it forms an acidic buffer. Okay. Now the point is, you consider this reaction here. This is what? This is a neutralization reaction. Acid and base gives salt plus water, right? Okay. Now if I give you one thing, here you see, if I give you 1 mole of this and 1 mole of NaOH, is this a complete neutralization reaction? Is this a complete reaction? If you take 1 mole of this, yes, because 1 mole of CH3COOH requires 1 mole of NaOH. So when you take 1 mole of both compounds, so there is no limiting reagent, both reactant will react 100% and converts into salt and water. Yes, Purvik, it is. Because you see the reaction is balanced. Right? Reaction is balanced. 1 mole of CH3COH react with 1 mole of NaOH. So this reaction goes towards 100% completion. CH3COH won't fully dissociate. Fine, that won't dissociate. But NaOH, there is one more thing here. 1 mole of CH3. See, it's not like we are not considering the dissociation here. See, Sukirth, we are not. CH3COH is a weak acid, correct? Dissociation won't be 100%, right? But that is true. That is true. This reaction won't be 100% complete. That is true. But I am just considering the amount here. Sometimes, you know what happens. Let me finish this, then probably you will understand what I am trying to tell you. Okay. Sometimes what happens here, see, for this solution, let me write down one thing over here. For this solution, you see, when the reaction takes place, right, the pH that you get for acidic buffer, the formula of pH that we can always find out, but I'll give you the formula directly now. Okay, that will be equals to pKa plus log of salt by acid, concentration of salt by concentration of acid. Okay, concentration of salt by concentration of acid, right? This is the formula we have. Salt means what? Let me write down this again. pKa plus log of, I'm coming back to this again. Okay, just give me a second. Salt is CH3COO minus and acid is CH3COOH. This is the formula we have. Right. Now you see what happens here when this reaction takes place. If you know the degree of dissociation of this, if it is given, sometimes in the theoretical questions, what happens, theoretical question I'm talking about, actually this will not dissociate because that is a weak acid, right? But sometimes in theoretical questions, they'll ask you whether this solution forms a buffer solution or not, right? Sometimes in the question, they'll give you that this is a acidic buffer, then you have to calculate pH. Then you know that, okay, acidic buffer we have, then we have to use this formula. Okay, directly you can use. But sometimes they will not mention you that the solution forms a buffer solution. Then you have to first analyze that whether it is a buffer solution or not. So suppose what happens, take an hypothetical situation here, right? If this CH3COOH reacts completely with NaOH, NaOH, suppose you have excess amount, right? Suppose the CS3COOH reacts completely with NaOH. Then in the solution, we have what? We have CS3COONA present. We have H2O, but we don't have this CS3COOH, right? And for acidic buffer, we require CS3COOH and CS3CONA both. So if the confusion is what, like, since you got this that it is a weak acid, won't dissociate, but sometimes what happens, they'll give you equal number of moles here, right? And they will not mention in the question that the solution is forming a buffer solution, right? And most of the time a student what does, they feel okay, one mole we have, so one mole reacts with this, so this will react completely, so there is no more CS3COOH present in the solution, hence the solution won't form a buffer solution. But that is not exactly true. If I give you suppose 2 mole of this, right, and 1 mole of this, right, so we know 1 mole reacts with 1 mole, so this 1 mole reacts with again 1 mole of this only. So 1 mole of CS3COOH left. So here we have 1 mole of CS3COOH and 1 mole of CS3CONA forms. So we have acetic acid also, and we have this salt also present, and whenever these combination are there, it forms a buffer solution, right? So that is the point I was trying to make. It is true that weak acid won't dissociate. Like some of you have said that yes, it will dissociate, right? It will form 100% neutralization is there, right? But the point is, if they have given equal number of moles, then also this particular thing forms a buffer solution, right? If the number of moles is different, then clearly you can say, like some of you have said, okay, this will react 100% and form salt, right? But if the number of moles are different, then you can understand, okay, some amount of CS3COOH is there and CS3CONA also forms. The solution will be a buffer solution, and then we'll apply the formula of buffer solution, pH of buffer solution, right? Sometimes in the question, what happens, they will tell you that this CS3COOH reacts completely with NaOH. We have excess of NaOH present, okay, and that makes the dissociation of CS3COOH possible, and there is no more CS3COOH left. In that case, you will use the formula of neutralization reaction, where the weak acid reacts with strong base. All these 12th class students, you must have done this neutralization reaction first. Strong acid, strong base, weak base, weak acid, strong base, strong acid, weak base. Like this, 4 possibilities are there. That's why you see this particular reaction is reversible in nature also. We should write down this sign here, because this also forms CS, but that is what, again, a different thing we have. But whenever you have combination of CS3COOH and CS3CONA, you have to keep this in mind, that the solution may form buffer solution, and the type of buffer solution is acidic buffer, and then you have to use the formula of buffer solution, which is nothing but this CS3CO minus and CS3COH, right? This is what the concept you have to keep in mind, because there are many formulas of pH. What formula you have to apply depends on what type of solution we have, right? So most of the time in the exam, they'll give you this, but they will not mention it is a buffer solution. So you have to identify, you have to keep this in mind and identify, okay, whether the solution is forming a buffer solution or not. Then you have to use the formula. Okay. Anyways, this is the one type of buffer solution we have, acidic buffer, which forms by the solution of weak acid and its salt with strong base. This is the formula we have, right? And CS3CO is a concentration of salt and concentration of acid, okay, at equilibrium. Now, basic buffer, you write down the second type of buffer solution here. That is basic buffer. And one more thing, when I take this revision class for ionic equilibrium, no, then I'll again discuss this. Okay, again we'll discuss it and see some questions onto this also. Okay, so you don't worry with this. We'll again discuss this, because we are not discussing now how buffer solution works, right? How they will neutralize the pH, how they'll maintain, how they tries to maintain the pH of the solution. That we are not discussing since we don't have time. But we'll discuss this in the class. when we take the revision class of this. Okay, so you don't worry with that. Okay, now next to write down the second type of buffer solution is basic buffer. Basic buffer. This type of solution forms by the combination of, it is a solution of weak base plus its salt with strong acid. Reverse, salt with strong acid. An example, weak base we have NH4Cl, right? And its salt with strong acid. Suppose we have um, weak base and its salt with strong acid. Suppose the salt of this strong acid is, I am taking suppose NH4OH. Sorry, NH4OH. I have written it reverse. This is weak base and salt with strong acid. Basically, weak base is NH4OH and strong acid, suppose I am taking HCl. Right? This also be a reversible reaction. Why? We'll discuss this later on. NH4Cl plus H2O. So this is the salt of weak acid and strong base. Weak acid and strong base. NH4Cl and NH4OH is a weak base, right? So whenever you have this combination, NH4Cl plus NH4OH, that also forms a basic buffer, right? And the formula of basic buffer is what? It gives a basic solution. So we write here POH. POH is equals to pKb plus log of concentration of salt by concentration of base. That is the formula we have. Okay, here also we have same thing. You have to analyze and see whether this NH4OH and NH4Cl is present or not in the solution. Then only we can say it is a basic buffer. Now one question only we'll discuss so that you can understand how to solve the question. Suppose the question is this. On this last question we are discussing on this, and then we'll see some concepts of GOC. Question you write down. You see, it is given CH3COH. In short, I'm just giving you data. CH3COH plus NaOH. See, they will not give you weak acid and its salt with a strong base. That is the point I'm trying to make. It is acid and base only. You have to analyze that in the reaction mixture whether the acid and its strong base is present or not. Okay, and another thing is given, it is 200 ml. Volume of this is 200 ml and volume of this is 100 ml. It is 0.1 molar and it is 0.1 molar NaOH. You have to find out the first thing, the pH of the solution. pH, if 50 ml of 0.1 molar HCl added. Third one, 50 ml of 0.1 molar NaOH added. In all these three cases, you have to find out pH of the solution. One more thing, Ka value is given. K value is 2 into 10 to the power minus 5. This is given. Tell me, if you understand this question, this is a very conceptual question. If you understand this question, you can understand buffer solution easily. Value of what, Sukrit? Sukrit, dissociation of CS. It is not given CS3COH PK. So that is not required, Sukrit, here. That is what you are having this doubt since a few things we haven't discussed in ionic equilibrium. That's why you're asking this. Okay, so we'll do this. Okay, wait.